Let's start today with the first keynote. As Robert was saying, if you feel the need for water, snacks, coffee at any time, just please wander off. That's fine. So welcome again. Hi, it's me again. So welcome to this talk on data aggregation for net zero power systems, or in other words, the status quo of the ERC project, Net Zero OPT, right now. So I'm the PI of this project, but obviously no researcher can work by him or herself. So this is why I took the liberty today to have my collaborators and my students on this project to give this keynote together with me. And I will take the opportunity to introduce the motivation for this research, talking about the dimensions of complexity for energy system models, and introduce the theme at the same time. So energy system models are complex because of a variety of different reasons, because there are very different dimensions to energy system models. And I see an uncertainty dimension, a technical dimension, a spatial dimension, and a temporal dimension that make energy system models complex. So uncertainty because, of course, life is uncertain. We have scenarios. This makes model size grow. Yannick is working on this. So Yannick is not speaking in this session, so go check out his poster later on. The other people who are there are going to talk today, and we're going to touch upon those different dimensions of complexity. So, for example, the technical one, how deep into the technical modeling are you going? Are you introducing unit commitment variables into your model? Is there some discreteness? How do you model storage? So this is something that Thomas does in his research. Then we have energy systems and we have energy grids. We have the power grid, or we have the gas grid, we have pipelines. So this is another dimension that blows up model size. And Benjamin is going to talk about this later on. And then last but not least, we have a temporal dimension, because a lot of these optimization models, they span across several years or even decades if you're going into the planning horizon. And the combination of all of these dimensions make what energy system models, what makes them so complicated. And on a temporal domain, Luca, Jakub, and I are working on it, and Luca and I are going to talk about this later on today. So what's on the agenda? What's on the menu for this particular talk? It's going to be pretty intense, but hopefully you will enjoy it as much as we enjoy this research. So I will start off with a motivation and the starting point that triggered that work. Then I will move on to how this can be extended, these time series aggregation methods can be extended to include a network and time linking, time coupling ramping constraints. Then Thomas will continue talking about how this can be extended to account for storage constraints as well. Then Luca will cover how we can bound the errors of these methods. And then Benjamin will go to a different realm, the realm of space, spatial aggregation, and then we will conclude. So you're in for a happy ride here. So why do we do this? Imagine your personal favorite digital twin of the power system. So we have one, and if we look at an annual problem with hourly resolution, then this might have up until like 630 million variables. And this takes quite a long time to solve. So if we solved a problem like this on the Frontier supercomputer, it would take around 18 days of computational time to solve this. Unfortunately, I don't have the Frontier supercomputer in my pocket. We don't have that kind of budget here. We have regular workstations and servers, and there this might be intractable depending on your level of detail, of technical uncertainty, and so on and so forth. And what we want to do in the ERC project, in the Net Zero OPT project, is we want to reduce the model size. We want to do data aggregation so that the model is considerably smaller, but you still get very high accuracy in the output. And because of that, you can solve this very, very fast on the Frontier supercomputer. But even more importantly, you can solve this on your own workstation. So everybody at home who is into energy system modeling could solve very large-scale problems on their own workstation. This is the goal. And how? What's the methodology that we're going to use here? The methodology is time series aggregation. And I remember, I think it was Leonard who told me last year, it's like, time series aggregation is so boring. And I was telling him, no, this is not boring time series aggregation. We're bringing sexy back in time series aggregation. And he was like, you should have told me this before, then I would have read the paper. So maybe now we're lucky enough for you to have read the papers. So what is your time series aggregation methodology? So essentially you start out with a time series of demand or wind or solar PV production. You take your favorite clustering algorithm, k-means, whatever, and then you compress this data into something that in the 80s used to be a load duration curve, or could be representative days or representative hours, as you see on the plot here, which will show up later on. Unfortunately, the traditional time series aggregation methods that most people use, if you're not very deep into this, they're input-based methods, which means that they try to find the best approximation of the input data, and not really taking into account the model itself when you do this data aggregation process. And most of these methods, therefore, also do not provide any error bounds, which means you work with aggregated data that later on you don't really know how the error is going to propagate through the model that you're using it for. And to give you a very simple example of this, we take an economic dispatch problem. So there are going to be a couple of equations here, but I know you're all very deep into this matter, so I know that a couple of equations are not going to scare you. So imagine you have a very, very, very simple optimization problem. Your indices G for generators and K are the time steps here. And what you want to do is you want to minimize overall system cost. So you have production, P production of generators G at time step K. This has a variable cost. You might have non-supplied power as well. You have a demand balance constraint where you say your demand at each time step has to be the sum of the production and potentially non-supplied energy. And your power operation has to be within operating bounds. So far, so good. So if you're then going to an aggregated model, then you have fewer time steps. So now here you have representative periods R, and usually the number of representative periods that you have is way smaller than your original set of time steps. And then your optimization problem, your corresponding optimization model looks very, very different to the original one, just that instead of having your full time series of demand, here you just have average demand for these representative periods and maybe some weights in your objective function. This is the general idea of these aggregated models. And let me give you a very simple example. So the model on the left, if you had 2 generators and 1 year in hourly resolution, it would give you around 26,000 variables, this model. If on the other hand, you took your aggregated model and you only took 3 time periods, then you would only have 9 variables, which is of course a lot smaller than 26,000. So now let's do this. Let's cluster our data. What you see here actually is a plot of your hourly time series of demand and wind. Every X is an hour, is a pair of your data for demand and wind. And then you say, k-means, please give me 3 clusters. So k-means does this, and these X's are the centroids of these clusters. And then you say, I run my aggregated model with only 3 time steps. And then what you will get from your aggregated model is very, very bad. So you get a 90% error in overall objective function value. And what's even worse is you completely miss loss of load with only these 3 time steps. And then you will say, of course, because 3 is ridiculously small, you cannot characterize this system with just 3 time steps. But the thing is, you can, actually. So in the Net Zero OPT project, what we have shown mathematically is if we cluster in a different way that you see here, so clustering according to, if you want to call it active constraint sets or simplex spaces, if you're a Danzig fan, for example, then you can actually you would aggregate differently. So you would aggregate hours where the system is in the same operative state. And you can prove mathematically that if you aggregate time like that, then you make a zero error in the objective function and in all of the model outputs. So actually with 3 representative hours, you can solve this system perfectly. And this means 9 variables can give you a perfect approximation of this system, as opposed to 26,000. And that's pretty good. So this was the starting point of this research. This is what's in this paper down here. And this idea triggered the ERC grant, and we thought, okay, well, maybe now we can scale this up to something that's a more large-scale problem and not really a toy example anymore. So let's move on and see whether this kind of approach would also extend if you include a network or if you include ramping constraints. We added a very simple formulation of a network into this economic dispatch, if you want, and then we looked at active constraint sets. So what you see here on the right are the different arising active constraint sets in this optimization model, and everything that's the same color, all of these time periods you can aggregate among themselves without losing any accuracy in the model. So having line constraints in this particular problem increases the number of active constraint sets that you have, but it doesn't invalidate the theory. So the theory still holds, which means that in this problem with 5 representative periods, you approximate the system perfectly, and you get a very big reduction in the size of variables that you have, which later on propagates through a smaller computational time, of course. And this you can find in David's paper. But really the most interesting thing to me at least was how to do time linking in this time series aggregation framework, because this is where it becomes tricky. So we started off with the simplest time linking constraint that we could think of, which is a ramping constraint, which limits the delta in power output over 2 consecutive time periods. And we said, okay, can we do something here to do time series aggregation? And the first thing that I want to do is I want you to look at the system matrix and the structure that the arising system matrix of a problem like this has. So K were our time steps, and everything here is the balance constraints and upper and lower bounds. And what you have down here in red, these are the coefficients that have to do with the ramping constraints. So in this matrix, actually, if it weren't for the ramping constraints, you could really disaggregate this matrix according to the time steps. It would fall apart. You have independent constraints here. But the ramping constraints, and especially if you look here, you have this -1 and 1 that connects together 2 different time steps, which a priori makes it impossible to disconnect the model and to disaggregate the large LP. So what we were saying is, okay, well, if we knew that at this particular time step, the ramping constraint wasn't active, if the constraint isn't active here, well, it's essentially as if you were to ignore this particular row of the matrix. And then there you could disaggregate this matrix and disaggregate, therefore, the large-scale LP and make it into smaller pieces. So this is the idea that we have used there. So we think of identifying when ramping constraints are going to be active. Once we have that, we can essentially take the full time horizon and cut them up into smaller different submodels, which can then be parallelized and solved independently. And that is something that a priori you cannot do with this large-scale LP, but you can if you identify when you can split this matrix. So then we could solve these in parallel, and once we have the solution of all of these independent submodels, we put them back together in the end, and then this is comparable with a solution to the full-scale model. So we applied this to a case study of the Austrian power system. This is Austria. Austria has 9 federal states that nobody cares about who is not Austrian, but we are here in Styria, so Graz is around here. And now the question is, how do you know when ramping is active? Because you don't know that beforehand. And that is fair. So the idea that David came up at the time of his PhD was to train a classifier. So if you train a classifier, which is just a binomial classifier telling you ramping is active or it's not active in this particular hour. He did this, and this classifier had an accuracy of 92%, which is pretty good for the classifier. We were happy. However, that's not the number that really matters. So the number that matters is if you use this classifier to split up the full model into smaller time pieces, how much error do you get in the submodels? And the answer is actually what you get is even better than this 92% accuracy. In the end, the total system cost error is only 0.004%. So this is very small. Total production decisions are also below 0.01% in comparison to the full model. Full disclosure, there is one error of around 18% in Tyrol, actually. However, that number, this production decision, is very small in absolute terms. So in the total Austrian system, that doesn't really matter that much, and it's very difficult sometimes to approximate things that are very small in absolute terms. But we tried this for 6 different weather years as well, and the classifier performed, and the methodology performed really well across all of these. And now what's even more important is, so how in terms of computational savings. So the full model here, it was an LP, it wasn't that large, so it took 115 seconds to solve. But in comparison, we split the model into 400 submodels, and theoretically, your bottleneck there is your largest submodel, and the largest submodel took 0.4 seconds to solve. So if you could parallelize this perfectly, then you go from 115 seconds to 0.4. Plus minus overhead of parallelization, right? Which is not 0, but in any case, so theoretically, this gives you a very big speed up because you have this possibility of disaggregating something that before you couldn't disaggregate. So key messages to take away from this particular part of the talk, which is about the network and ramping, is that you can still do exact time series aggregation, meaning that the model outputs that you will get with your aggregated model are exact if you have a network, if you have ramping, and this idea of disaggregating the temporal scope, so you get these submodels that you can then solve in parallel and get back together in the end, and aggregate back together in the end, leads to very, very good computational times of the models. So those are the corresponding papers for that. And without further ado, there will be a little bit of ado because we have to switch the microphone. We will switch over to Thomas, who will tell you about storage.
Okay, while I'm trying to figure out how this thing works, I think you can hear me. Excellent. So I want to pick up where Sonja left off and investigate together with you if we can extend those results to storage technologies. So picking up where Sonja left off, in terms of ramping, what we're faced with is inequality time coupling constraints, and they can be active or inactive by definition. However, when we start looking into energy storage, we're talking now about equality time coupling constraints, basically the state of charge inventory constraint of the storage unit. And by definition, this constraint is always active, so meaning during all of periods of our energy system optimization model. So now the questions that I want to investigate together with you is exact time series aggregation with storage equality constraints still feasible? Can we make it? What are the criteria for achieving this? Can we disaggregate the problem and further aggregate it? And how can we implement this in practice? So here you see the corresponding energy system optimization model. This is an operational problem, very simple single node problem again. And I want to put your focus on this equality constraint here, representing the state of charge balance. And again, we're looking into the system matrix here, where indicated by these red coefficients, you can see that we get some time coupling, and this time coupling, however, is only associated with the state of charge variable in the time step now, linking the time step, the previous time step. So what we have observed is that exact disaggregation into independent submodels that then can be solved in parallel is possible when the state of charge of the storage unit is 0 in 2 consecutive time periods, or at least 2 consecutive time periods. And what this gives you is a potential for parallelization. So now putting this a little bit into a graphical context, here you see a result of the energy storage state of charge from a previous model run. And this can be split up into different active constraint sets that characterize different states of the storage. So whenever we are in this state that is represented by the active constraint set number 1, where the state of charge is 0, we get what we call unlinked submodels. So we can disaggregate into unlinked submodels here. And then whenever the state of charge is different from 0, what we end up is linked submodels. And within those linked submodels, when we're in the same active constraint sets indicated by the colors here, for example, storage being at an idle state and the renewable technology being the marginal generator, for example, we can further aggregate within those linked submodels. And therefore, this aggregation is represented by those weights indicated here. So what we came up with is a conceptual 4-step argument to show numerically that exact time series aggregation with storage is still possible. So what do we do to achieve this? First, we cheat and we solve a full-scale model, which has 8,736 time steps in this case, to identify our active constraint sets and corresponding dual information. Then we disaggregate the model into unlinked submodels and linked submodels, thereby, just in this disaggregation step, achieving a theoretical 24-fold reduction in computational burden, where we measure the computational load in terms of work units. And this represents the lower bound if we do perfect parallelization. Then, in a follow-up step, we go into the aggregation within the linked submodel. So whenever we are in the same active constraint sets, we aggregate those periods together. And in the end, what we get is that we get a time series aggregation that only has 933 periods that achieves 0 error in all the model outputs. And if you could perfectly parallelize the solution here, or the model runs here, you would achieve about 370-fold reduction in the computational burden. This is a theoretical result showing that it is possible when you have perfect information. But what should we do when perfect information is not available? Again, we have decided to go into machine learning there and training a random forest classifier for the disaggregation. So basically the classifier tells us, is the state of charge of the storage at 0 or is it not? And then we further go into aggregation where we apply some hierarchical clustering technique. And here you see results for different combinations of renewables and storages, being a battery combined with solar, pumped storage hydropower, going into the regime of long-duration energy storage with solar, and the same combinations with wind. And what should be the takeaway here in terms of the results is that you get relative small output errors, which depend on the number of clusters, particularly in terms of the objective function value. So here the range is -5 to -1% in the objective function values using only 30 clusters. And 30 clusters meaning the longest submodel that you have to solve, when you solve the submodels in parallel, has 30 time steps compared to the 8760 from before. And the computational speed up that we were able to achieve was between 20 and 120-fold. What are the key messages from this talk to take away? First of all, the Net Zero OPT project has demonstrated that exact time series aggregation with energy storage units is possible. And here we are leveraging disaggregation which enables parallelization and further aggregation to compact the problem size. In future research, again, this is somewhat of a very simple toy problem. We are planning to extend to problems with investments, multiple storage units, then the splitting becomes more tricky, and also longer duration energy storage technologies. And we are also looking forward to investigate other ML-driven approaches for the disaggregation and also the aggregation. And here, if you're interested in this topic, check out our paper that we recently submitted. And with this, I want to hand over to Luca for the time series aggregation with bounded errors. Put it in your pocket and on one ear.
Like this?
Yeah.
I think you can hear me also without, but... Ah, okay. No. Okay, thank you. Yeah, so hi everybody. Thank you all for being here. My name is Luca, and today I will present the next 10-15 minutes our research on time series aggregation with bounded error, or performance bounds, performance guarantees, if you want to call it in a fancy way. And specifically, we'll discuss 3 different topics. How do we enforce bounds when performing time series aggregation on the optimal objective function value of the full-scale model through the derived aggregated model? How do we enforce bounds on partitions of the optimal solution or the whole optimal solution space? And finally, I will give you a little bit of an overview on how we are trying to translate this concept of performance guaranteed time series aggregation from static optimization to optimal control theory. So let's start with some motivation. Well, if you are familiar with the framework where time series aggregation is usually applied, normally we have a full-scale optimization model, large-scale model in static optimization, where we use some input time series, for example, forecast of energy demand, renewable power generation, or market prices. If the full-scale optimization model is too large or too complex from a mathematical point of view to be addressed directly, then we can use time series aggregation, normally leveraging some clustering techniques like k-means, to derive an aggregated counterpart of the original input time series, now defined over a reduced set of representative time periods. We feed this aggregated time series into the aggregated optimization model, and then we solve the aggregated model in place of the full-scale one. Very nice. This works very smoothly, but there is a problem, actually, and it is the fact that we have absolutely no idea in this traditional framework whether the aggregated model is a good approximation of the full-scale one or not. So there is no performance guarantee, and it is quite important if you apply this in a practical setting, right? So what we try to do to address this problem is, let's say, trying to evolve time series aggregation towards something that is theoretically guaranteed to some extent or bounded in its error. And for this, we developed a number of theoretical results, and specifically the fact that if you construct the aggregated model as we describe in our papers, you can always enforce the fact that you will get a lower bound on the optimal objective function value of the full-scale model from the aggregated one. Now, the way you construct the aggregated model to enforce this theoretical property will depend on the nature of the original full-scale model, whether it's convex, non-convex, if it is a model with integer variables or constraints, and specifically the results that you see here comes from this paper where we consider a mixed integer linear generation expansion planning model, where the binary variables are on the first stage at the investment level. But the underlying idea is that you need to verify 2 different things and construct the aggregated model to enforce these 2 different things. The first one being the fact that every feasible solution to the full-scale model maps to a feasible solution of the aggregated model, while retaining the same objective function value. And this is, for example, normally guaranteed if you just take the mean-based classical aggregated model in the linear case, or also in most convex cases when you consider this type of aggregated models. And being the aggregated model a relaxation of the full-scale one, if you want, the feasible region contains that of the full-scale model, even though you cannot say contain because these models have different dimensions since we are aggregating, but just to give you a visual idea, then you will always get a lower bound from the aggregated model on the optimal objective function value of the full-scale one. Now, how do we use this in practice to derive these performance guarantees? Well, we have an algorithm for that. Again, in this case, it's applied to this mixed integer linear investment planning model. I won't go into the details. You can find it in the papers. We basically have two steps. It's an iterative algorithm. We are trying to estimate the true optimum of the full-scale model, the true value of the optimal objective function value. Through the iterations of the algorithm, we progressively increase the number of clusters. For example, let's say we start from k equal to 5. In the first step of the algorithm, we perform time series aggregation with any clustering technique. The results that I showed you, the theoretical results, holds for any clustering technique. It's about the way you construct the model, not the way you perform time series aggregation. And from that, we get a lower bound. Then, by projecting the lower bound onto the original full-scale model feasible region, in this case, fixing the binary variables and solving the underlying operational problem in the original full-scale investment model, you get an upper bound. We increase the number of clusters, compute again the lower and upper bound, again and again. At each iteration, we measure an optimality gap, the relative difference between the upper and lower bound. And when this optimality gap falls below a given threshold, the algorithm has converged. And we can enforce some nice properties given these theoretical results. For example, the fact that the lower bound comes from a reduced version of the mixed integer model through time series aggregation, and it holds for any clustering technique, as I was saying. And also the fact that, and also the fact that the upper bound comes from a linearization of the original mixed integer model, and it always provides a feasible solution to the original full-scale investment model. Now, in terms of results, this also works quite well. We tested it for a number of clustering techniques, k-means, k-medoids, GMM. As I said, the bounds will always hold. Of course, their convergence will depend on the specific clustering technique employed, but the performance guarantee is always retained. And also in terms of computational effort, it performs quite well, bringing over 50% computational savings compared to addressing the full-scale model directly. Now, you can check all the details in the paper, optimal virtual power plant investment planning via time series aggregation with bounded error. Now, everything that we saw till now in this part of the talk pertains only to the optimal objective function value. What happens if you want an indication about the optimal solution space of the model, partitions of the optimal solution vector? Well, we summarize this research question with the very fancy, cool title of this slide here. It comes from Sonja, actually. What are we clustering for? Meaning, what is the specific metric that we are interested into approximating when doing time series aggregation? And it is quite a common problem. If you think about, again, the investment model, this will be probably used by different stakeholders, for example, wind investors, storage investors, grid operators. And each one of these stakeholders, they have their own metric of interest while using the same model to, let's say, to model the evolution of the power system. For example, a wind investor might be interested in the minimum level of its investment in its wind units. That makes the investment planning model, the global one, optimum, right? So to find this, the optimal value for these metrics, we can actually use the objective function bounds that we developed through the algorithm that I just showed you. If you go back again to the objective function bounds, from a mathematical point of view, these questions means finding the solutions within the upper and lower bound when the algorithm has converged that minimize or maximize the given metric of interest. We can formulate these as optimization models, maximize or minimize the metrics subject to the full-scale dynamics, the dynamics of the original full-scale model, while now we enforce as constraints that the global objective function of the original full-scale model has to lie within the upper and lower bounds that we have derived through the algorithm. And this not only helps finding the optimal range of the metrics that retains the optimality gap that we managed to came up with through the algorithm, but also helps reducing the feasible region of the full-scale model, which in the case of a very complex model can help also speeding up the computations. This is an example on how this thing works. Just to give you an idea, here you will see on the left-hand side of the slide the objective function bounds, while here you have the bounds derived for a stakeholder-specific metric, in this case the investment in a specific storage unit. And the way we read this is if you take, for example, this point here, so at the early iterations of the algorithm, the stakeholder is already informed that they will have to invest at least 0.25 megawatts in this specific storage unit for the investment problem to have this optimality gap. Okay, so to be optimal within this range here. That is how we interpret the result. And you can find all the details in this paper. What are we clustering for? Establishing performance guarantees for time series aggregation in generation expansion planning, where we extend the theoretical results to mixed integer quadratic formulations with storage constraints, the lower bound result. We discussed this research question of what are we clustering for, and we also provide a very nice comparison, if you ask me, with Bender's decomposition, which is indeed quite similar to the algorithm that I just showed you. Now, in the last part of the talk, I would actually would like to discuss a little bit a very interesting application that this performance guaranteed time series aggregation method can have in optimal control theory. In this case, the motivation is not anymore the fact that the model might be very large. It's more the fact that we need to compute fast reactive control decisions in real time online at very high temporal resolution. In control theory, this problem is very common and is usually addressed with a very popular type of controllers, which is called model predictive control. If you're not familiar with the topic, I'll try to give you a very short overview. This is, you can think about it as an online optimization tool, even though online optimization is something different, but let's think about this in this way. The controller sends control actions to the power plant at each iteration, at each time step. It measures the output of the power plant, it updates the control action, and this works online progressively at each time step. Within the model predictive controller, we have an optimizer, which is considering a prediction horizon, so predictions for the next 10, 15, 20, 100 time steps. There is the optimization horizon. The control actions and the state of the power plant are optimized over the prediction horizon, but then only the first control action, the control action computer in the first step of the prediction horizon is applied to the power plant. We shift the prediction horizon by one step, we recompute, we apply only the first control action, and so on and so forth in an online setting. Now, this provides quite an interesting application for time series aggregation, because if the prediction horizon is within the prediction horizon, we have a number of time steps over which this optimization will be computed several times, right? Since we are shifting the horizon only by one step at a time. Meaning that with time series aggregation, we could, for example, retain full resolution in the very initial part at the starting of the prediction horizon, while aggregating the tail of the horizon, where we will have time to modify and update the control action. And this works quite well in practice. In a way to enforce let's say, the performance guarantees that I just mentioned, so retaining these properties while reducing the prediction horizon, which can help, of course, crushing the complexity in the temporal dimension of this problem. And the nice thing is that you can also combine this with other popular approaches for reducing computational effort in other dimensions or layers of the control problem. For example, in a number of assets or scenarios, the dimensions that Sonja mentioned at the very beginning of this talk. And we did that, actually. We combined time series aggregation with distributed control, specifically augmented Lagrangian relaxation, to address simultaneously all the complexity dimensions of this controller while retaining the performance guarantees that I mentioned before. And you can find this in this recent paper that we just submitted to PSCC, distributed stochastic model predictive control with temporal aggregation for the joint dispatch of cascaded hydropower and renewables. Here we combine time series aggregation, model predictive control, and distributed optimization, distributed stochastic optimization if you want, ADMM if you're familiar with this topic. With the distributed part, we decouple the problem in its asset dimension, so per hydropower plant within the cascade, and in its scenario dimension, in its uncertainty dimension, so per scenario. We combine it with time series aggregation to compact the temporal dimension of the controller in a way that we crush this complexity in all the dimensions of the MPC problem. And with model predictive control, we can do this online in a optimal control setting to control these systems in a fast, reactive, and performance guaranteed way. Just to give you some key messages now before I conclude. Time series aggregation is a very useful tool for helping restoring tractability in complex optimization models, also in optimal control theory, as we've seen. But the problem is that traditional time series aggregation are normally heuristic methods, or they heavily rely on heuristics. What we do within net zero opt within this, let's say, track of the research on performance guarantees is to enforce bounded error when applying time series aggregation, both in the objective function and in the optimal solution space, while also providing a unified framework for time series aggregation that you can apply both to static optimization and optimal control theory. And these are the papers. You can find all the details there. So, yeah, please do so. It's quite fresh research. So if you have any comments or questions, I will be more than happy to discuss it with you. Thank you very much. And with this, I will hand over to Benjamin. You need to put this in the pocket. Do you need help? Put it on.
I'll try. I think it should work. So, thank you very much. For my part of the talk, I'm gonna switch now from time series aggregation to grid aggregation. So, in the end, we still have like the same goal of reducing the complexity of our energy system optimization models, and in grid aggregation, we face a different problem. So very often we have very large grids. For example, in this case, if we consider the European high voltage electricity grid, we have multiple thousand nodes in the grid data, and therefore it will be very hard to solve this with a lot of time steps. Then we have a lot of variables. And the goal of the grid aggregation is to reduce the size of the grid, so the number of nodes and also the number of lines. So we have a reduced version of the grid and can solve it faster and more efficient in our optimization models. A short definition about grid aggregation. The process of grid aggregation divides up into two parts. So the first part of grid aggregation is like the partitioning of the nodes. So how are we going to partition the nodes of our full grid? which we want to combine or aggregate in the aggregated grid version. There are different approaches how to do it. So you can do it based on like general attributes of your grid, for example, like geographical distances or similar. You also can do it on electrical distances. And for my talk, I'm going to focus on dual-based partitioning methods, which are based on LMPs and NCP, which I will explain in the upcoming slides. And the second part of grid aggregation is the actual aggregation part, so how we are building a reduced version of our grid and how we are defining the equivalent parameters of our aggregated lines. There are also multiple different ways of how to do this. I think a very common one is like the parallel reactances, so just keeping the lines which connect our groups of nodes and then combining them together and create one equivalent reactance of those lines. But I'm going to only use the reduced PDDF approach to create a reduced version of our grid. At first, I'm going to have a look at I'm going to show some different clustering-based partitioning approaches and show some results there. And then I'm going to go into detail on how the partitioning, why the clustering approaches are not working all the time very good, and how we think we could improve the performance of the partitioning part. So first, how are we going to partition our nodes into groups which we want to aggregate? Typically, this is often done based on locational marginal prices, because we have them, often we have them as model results, as the constraint of as a dual of the constraint of the nodal power balance. And there are multiple approaches how to cluster them. So basically, we can cluster them by a k-means clustering algorithm, but also by a spectral clustering or ANEC, which both take into account the topology of the grid, so which nodes are connected in the network. And we have came up with another clustering metric, which we call the network congestion price. And in the network congestion price matrix, we combine the PDDF matrix, so the power transfer distribution flow matrix, with the information of the line limit duals. And therefore, we get a matrix with the information of the congested lines for all of the nodes in the grid. Because in this approach, we want to try to keep as much congested lines from the full grid in the aggregated grid, because we assume that the information of the congestion is very important for the actual solution of the model. And we are also going to cluster this NCP matrix with a typical k-means clustering algorithm. Now have a look at some results of the partitioning. So since the goal is to keep as many congested lines in the aggregated model, it's good when the red lines are between different colors, because then there are actually in the aggregated grid. But for example, in this case, this would be not so good because the information of the congested line gets lost in one aggregated area of the grid. Which is also not a very good behavior. We can see here is that, for example, when we cluster only by k-means, there are some nodes which are not directly connected to one another, which is also a not wanted behavior of the clustering. If we have a look at the NCP clustering, we have a kind of similar performance to the ANEC clustering, which is quite good. And I'm gonna come to the point why it's still better than the ANEC in terms of performance. We have also tested this for some actual models, so reoptimizing the model with an aggregated version of the grid. In this case, we have done it for the IEEE 300 bus system, and we're going to have a look at the models with 50 nodes in the aggregated model down to 1 node in the aggregated model. So this is just a slice of the result, so to say. And we can see that the clustering based on the locational marginal prices with k-means does not a very good job, because if we consider our single node case where we don't take any grid into account as the worst case scenario of aggregation, it's even worse than that. So this aggregation doesn't make any sense, I would say. Also, the spectral clustering performs better, but reaches the level of error than the single node case very early. So also not a very good aggregation. And the NCP k-means and the NEC clustering perform comparably well. Why do we still think that the NCP k-means has an advantage? It's faster than the NEC clustering because the NEC is an iterative process and therefore takes more time to do the clustering or the partitioning process. In this graph, we still see that all of the aggregation methods have some error, and we wondered why there is so much error and what we could do else. Therefore, we did a greedy exhaustive enumeration, in this case, of the IEEE-24 bus system. So we started with the full grid model. We tested all of the possible combinations based on the lines in the grid, re-optimized those aggregated models, and then chose the model, so the aggregated model with the least error. So for example, we used the objective function value error or redispatch cost error, and then we sticked to this one aggregation, and then took the next turn with like 23 nodes and this down to 1 node. And when we have a look at the results, we can see that it's possible to aggregate the model actually down to only 9 nodes and still have the same unit dispatch in the aggregated model compared to the full model. Why is this the case? So if we have a look at the partitioning of the 24 bus system, we can see that there are some of the nodes kept individually, so not assigned to another group. There are still some groups of nodes, for example, the blue one or the orange one, which include multiple nodes, but there are some of the nodes kept individually. Why is this? Because at those nodes, there are some generators located, which are actually restricted of the grid in the full grid model, and therefore the nodes don't get aggregated, because otherwise the impact of this congestion on the generator would change, and therefore the unit dispatch also would change. So it would be important to keep those individual nodes with those generators separated from the aggregation. So therefore we have lower errors in our aggregated models. This brings me already to the key messages. So we should consider the network topology in all of our grid partitioning methods, and only based on like line congestion information, the clustering doesn't perform very well, and therefore our future research will be to find another way of partitioning the nodes and also taking into account those restricted generators by the grid. And the last point is, check out my paper. So with public, this is the part of the now I'm getting nervous because the part of the clustering-based partitioning is public in this paper. So if you're interested in, check it out.
Yeah, excited. Thanks. So we're not so much on time anymore. But I will go quick. So this is to sum up. You have seen a lot of things. This has been very intense. Energy system models are very cool, but they're super complex and there are many things that you could do. Don't do your plain vanilla input-based methods, because there is a big aggregation potential that you might leave untapped there. So in our research, what we have tried to do is to leverage this potential to essentially get more bang for your buck. So to solve better, more accurate models with the same model size, to show that it's actually possible to do exact aggregation, even if you have a grid and if you have time coupling constraints. We use ML sometimes to help us out there to guess when certain things are going to happen. And we provide a framework that gives you performance guarantees in this room full of darkness that is energy system modeling and aggregation. Apart from that, we're having a lot of fun doing this, I have to say as well. So thanks a lot for the attention. This is the QR code to the website. I am going to take questions, but please go and have coffee as well, because we didn't stick to time so much. But happy to take any questions now. Thanks a lot.